Hello everyone. Today I'm here with a new video. In the next few videos, I want to discuss linear algebra and its significance in control theory, especially in modern control systems. Since the topic is more mathematical, I plan to present the material in 3 or 4 videos. Each video will focus on a specific aspect of linear algebra. In the first video, we will start with concepts of linear space, also called vector space. Now, let's briefly review what we covered in the previous session. We start with state equation and output equation in a state space, focusing on their nonlinear forms. Then we define our control object, tracking control. Our goal was to design a control input such that the system output accurately follows the reference signal. We next discussed the idea of trajectory design. In trajectory design, we create a nominal trajectory and a nominal control based on desired output or nominal output. A nominal output is simply the output that matches the reference signal. As I mentioned before, this course is not about trajectory design. That's a separate course of its own in every branch of engineering. Here we assume that the nominal trajectory are already given based on the reference signals. After we studied the behavior of trajectory near the nominal trajectory in the state space. Together, we derived the perturbation state equation. This equation had 2 parts. A linear term involving the perturbation state and control, a set of high-order terms forming an infinite series. We assume we are around nominal trajectory. Then our state is equal x bar nominal trajectory plus a perturbation term. And it's also valid for our control input. We divide our control input as 2 terms. One term is nominal control and another term is perturbation terms. To analyze this, we borrow a theorem from nonlinear dynamical system theory. It tells us if the nominal trajectory is an equilibrium point, then it's sufficient for perturbation state delta x converge to 0. If that happened, the entire nonlinear system converges to the nominal trajectory, or nominal trajectory is asymptotically stable. Equivalently, the output signal follows the reference signal. Finally, we discuss the arbitrary reference trajectory case. From the nonlinear dynamical system theory, we know that for the perturbation system, the linear part must converge to 0 exponentially. If the norm of delta x of t decay exponentially, then the system is asymptotically stable. I mean the nonlinear nominal trajectory. For this condition to hold, our control input must satisfy a key constraint, this constraint. When delta x of t is equal 0, delta u of t should be 0. This makes sense because we split the control into 2 parts. The nominal part u bar and the perturbation part delta u. If the system state equals the nominal state, then the control must also equal the nominal control. This ensures that the output remain equal to the nominal output, which itself follow the reference signal. So, in summary, we showed that a nonlinear tracking problem can be recast as a linear regulation problem. Why linear regulation? Because in linearized system around nominal trajectory, we want the perturbation terms to converge to 0, meaning the equilibrium point at the origin is asymptotically stable. In the next step, we explore the behavior of a linear control system. We derive the general solution of a linear system and saw that it has 2 parts. The 0 input response, which depends on the initial condition, and 0 state response, which depends on the input. Both terms are expressed using the state transition matrix phi. For a time-varying system, phi comes from solving an ordinary differential equation. For a time-invariant system, the state transition matrix is simply e to the power of t minus t0. Next, we introduce the idea of state feedback. Why do we use state feedback? Because it creates a direct linear relation between the control and the state. With this approach, one of our main constraints satisfied. When delta x is equals 0, delta u is equals 0. When we substitute this feedback into uh, the linear perturbation system, then transform into the homogeneous linear system, whose solution is simply the zero input response, the new augmented matrix A of C. The corresponding state transition matrix phi again comes from an ODE if the system is time varying, and reduced to the matrix exponential if the system is time invariant. Finally, we connected this to our main objective, ensuring asymptotic stability of nonlinear system around nominal trajectory. With this step, we reduce the nonlinear tracking problem to a simple linear system. We know that the trajectory is asymptotically stable. For equilibrium condition, we just need to state transition matrix converge to 0. But for an arbitrary nominal trajectory, when our linear system is a time varying system, if the norm of a state transition matrix decay exponentially, then the perturbations vanished and the nonlinear system converged to its desired trajectory. After this brief review, it's now time to address an important question. Why do we need linear algebra in control theory? We said earlier that a nonlinear system is asymptotically stable if its state transition matrix converges to 0. For an equilibrium point, this simply means converge to 0. For an arbitrary nominal trajectory, it means the transition matrix must decay exponentially. This arises the question, can we design K of t such that the state transition matrix always converge to 0? Let's look at a simple linear system as an example. Our system has two states, so the feedback gain has two parameters, K1 and K2. When we apply state feedback, we get delta U is equal minus K1 delta X1 and K2 delta X2. When we substitute this into the state equation, we find that the dynamic mix of the first state depends on K1 and K2. However, the dynamic of the second state are completely independent of K. This means that no matter how we choose K1 and K2, the second equation remains untouched by control. The second state always grooves and the control input cannot influence it. This illustrates an important point. Sometimes, based on the structure of A and B, certain states are uncontrollable. In the other word, our control input cannot affect them. This naturally leads us to the concepts of controllability subspace of A and B. For small system like a two-state system, we can check controllability by direct inspection. It's easy. But for a large system, we need a systematic method to determine whether all states are controllable. And this is exactly where linear algebra becomes essential. To answer these questions, we need to understand the idea of subspace, and we need the tools of linear algebra to formally analyze controllability. Now, let's dive to another challenge. In practice, not all states delta x are directly measurable. Instead, we measure outputs. This means we often have to use output feedback laws, such as delta U is equal minus ky delta y. By using the output equations, we can rewrite this in terms of delta x. U is equal minus kt delta x, but delta x is a function of output equation parameters and ky. This leads to the main question. Here, we will not design k, we design ky. The question is that is always possible to design ky so that we can control the systems, or equivalently, can our control input influence all of the state, even though we only measure the outputs? In this point, you might ask, why should we care about the states if we are already tracking the outputs? The reason is that in a tracking control, we want to output follow the reference smoothly. If the output follow the reference while some hidden states diverge to infinite, then the system will eventually collapse. Tracking requires both the output follows the reference and the internal state remains well behaved. Let's see a very simple example. Suppose we have a two-state linear solution where the output depends only on the state, not directly on control. So in the general form of this, the output equation, delta u is equal c delta x plus d delta u. Here, d is equal 0. If the output is only one measurement, says delta y is equal delta x1, like this system, then the feedback law become delta u equal minus ky delta y or ky delta x1. And when we substitute this into the state equation, we see that the control affect both state equation. However, there is a problem. The equation for delta x1 is influenced by the control, so we can shape its behavior. But the equation for delta x2 essentially grows on its own. In fact, once delta x1 converges to 0, the control disappears and delta x2 grows forever. This means that while the output delta x1 converges to 0, so the reference seems tracked, the system internally becomes unstable because delta x1 diverges. This example motivates the concepts of observability subspace of A and C. In output feedback control, we don't have directly access to all states. We only see outputs. The observability subspace tells us how much information the outputs provide. Can we reconstruct the state from the outputs? If not, then we need to check whether the uncontrolled states are stable on their own. This is extremely important. A systematic method for investigating such questions, whether all states can be estimated or whether hidden states will destabilize the system, require the tools of linear algebra. Before we go into details, you need to understand what we mean by space. The space that linear algebra studies in depth. The most fundamental concept in linear algebra is the linear space. Also call it a vector space. In this course, I will use these two terms interchangeably. A vector space is always defined over a field. A field is an abstract mathematical structure, so don't worry about the full formal definition of a field. We will always mean real or complex numbers. Now let's define the vector space. A set V is called a vector space over a field F if it's equipped with two operations, vectors addition, a scalar multiplication, where a scalar is an element of the field. The set must be closed under these two operations. If you add two vector in V, then the result also be in V. If you multiply a scalar from F by a vector in V, the result must also be in V. In addition, these operations must satisfy some important axioms. For all u, v in V and alpha and beta in F, it should satisfy distributivity over vector and also distributivity over scalar. Also, it should satisfy associativity. Let me give you a simple example. Rn and Cn, the space of n-dimensional real or complex vectors. If you add two vectors in Rn, the result is still in Rn. If you multiply a real number by a vector in Rn, the result is still in Rn. It's easy to check that distributivity and associativity also hold. Vector space are not tied to geometry. They are abstract structures defined by these axioms. For example, the set of all real polynomials of degree less than n also forms a vector space. It satisfies closure, addition, a scalar multiplication, and the axioms. We will see examples like this soon. In control theory, most of the time we work with finite dimensional vector space over the reals or complexes. To summarize, a vector space is simply a set, together with addition and scalar multiplication, that is closed and satisfies a few natural axioms. This concept will be the backbone of much of what we do in the modern control. What is a subspace? Let V be a vector space over field F. We show vector space like this. It shows V is a set and F is our field. A subset Y of V is called subspace if together with the same operations of addition and scalar multiplication is itself a vector space over F. For example, R2 can be seen as a subspace of R3 because R2 is subset of R3 and it forms a vector space over field R. So R2 is a subspace of R3. And it's also R3 is a subspace of R4. Next, let's talk about linear dependence and independence. Is there any way we describe one vector as a linear combination of other vectors? For example, we have x1, x2 to xn. All of them are member of vector space. These vectors are linearly dependent if there exists scalars a1, a2 to an in F, not all zero, such that a1 x1, a2 x2 to an xn is equal 0. In the other word, at least one vector can be written as a linear combination of other vectors. And the set is linearly independent if the only solution to this equation is a1 to an is equal 0. It means we cannot explain or define none of these vectors as a linear combination of other vectors. It shows these vectors are linearly independent. For example, assume x1 is 1 and 1 and x2 is 0 and 1. Then suppose a1 x1 plus a2 x2 is equal 0. This implies a1 equals 0, a1 plus a2 is equal 0. From this, a1 should be 0, and if we put this here, a2 also should be 0. It shows x1 and x2 are linearly independent. Why do we call Rn as an n-dimensional vector space? The dimension of a vector space V over a field F is defined as the maximum number of linearly independent vectors in V. This leads us to the idea of a basis. A set of vector v1, v2, vn, subset of V is called a basis of V if it satisfies two properties. A spanning property, every vector x in V can be expressed as a linear combination of the basis vector. It means x equal x1 v1 plus x2 v2 to x and vn. Xi are a scalar in F, and linear independence. Vector v1, v2, vn are linearly independent. From these two properties, we can state an important theorem. In an n-dimensional vector space V, any set of linear independent vectors forms a basis. This means there is not just one basis for a vector space. In fact, an n-dimensional space has infinitely many possible bases. So the choice of basis is not unique, but the dimension is always fixed. So far, we have seen that a vector space can have infinitely many different bases. Depending on the chosen basis, every vector can be expressed uniquely as a linear combination of those basis vectors. Formally, if v1 to vn is a basis for a vector space V, then any vector x can be written uniquely as a x1 equal x equal x1 v1, x2 v2 to xn vn. And xi are scalar in F. x1 to xn is called coordinate representation of x with respect to the basis v1 to vn. For example, R2 has dimension 2, so every basis has exactly two linearly independent vectors. The standard basis is 1, 0 and 0, 1. Any vector x equal x1, x2 can be written as a x equal x1 v1 plus x2 v2. So its coordinate representation relative to the standard basis is simply x1, x2. Now consider another basis. V bar 1 equal 1, 1 and V bar 2 is equal 0, 1. Earlier, we proved these two are linearly independent, so they form a basis for R2. Any vector x can also be expressed as a x equal alpha 1 v bar 1 plus alpha 2 v bar 2. And alpha 1 could equal x1 and alpha 2 could equal x2 minus x1. So, with respect to new basis, the coordinate representation is x1, y1, x1, x2 minus x1. This shows that while the vector itself doesn't change, its coordinate representation depends on the choice of basis. Then we can represent the same vector with different coordinate representation. Up to this point, we have seen that the same vector in a vector space can have different coordinate representation depending on the choice of basis. Now, suppose we have two different bases, v1 to vn and v bar 1 to v bar n. And for each of this, we have different coordinate representation of x1 to xn and x bar 1 to x bar n. Or more compactly, x equal v bar v1 to vn, x1 to xn equal v bar 1 v bar n, x bar 1 x bar n. There is a key question. What's the relation between the two coordinate representation vectors? In the other word, how do we systematically move between different coordinate representation of the same vector? This question leads us directly to the concept of the change of basis matrix. To define the change of basis matrix, let's start by expressing each basis vector vi in terms of a new basis v bar 1 to v bar n. So for each vi, we can write coordinate representation as a P1i to Pni. It's the coordinate representation of Vi with respect to V bar 1 to n. We can represent Vi in this form, and if we assume this part is V and this part is Pi, then we have a relation between Vi, V bar, and Pi. We know the matrix V1 to Vn is this, and instead of each of Vi, we use this equation. And we can factor out V from this matrix, and we have V equal V P1, P2 to Pn. And we know V is V bar Y to V bar N. Then we have the relation between matrix V1 to Vn with V bar 1 to V bar N and P. When we use this equation in both representation of X, we have two representations for X, one in V and one in V bar. And instead of V, we use this equation here. Then we can represent, here we have V bar, here we have V bar, then this part should be equal this part. And here we define X bar with respect to X. P is the change of basis matrix that converts the coordinate representation of vector from the basis of V1 to Vn to its representation in the basis V bar 1 to V bar n. And also, each clone of P is simply the coordinate representation of the old basis vector Vi expressed in terms of new basis vector V bar 1 to V bar n. Now let's review all the concepts we have defined so far with an interesting example. Consider the set R4, which is the set of all real polynomial of degree less than 4, where x is the independent variable of the polynomial. First of all, I want to show that the pairs of R4, X, and R forms a vector space with the usual polynomial addition and scalar multiplication. The sum of two polynomial of degree less than 4 is still a polynomial of degree less than 4. Also, multiplying polynomial of degree less than 4 by a real scalar doesn't change its degree. And also, to check, we can easily check every two polynomial in R4X and alpha and beta from R satisfy distributivity over vector over polynomials, distributivity over scalars, and associativity. Thus, R4X and R is indeed a vector space. If we assign v1 equal x3, v2 equal x2, v3 equal x, and v4 equal 1, it's not hard to show that these are linearly independent. Every polynomial of degree less than 4 can be represented uniquely as a linear combination of these three bases. So R4 is a four-dimensional vector space, and also we can show coordinate representation of each polynomial with respect to these three bases. For example, this polynomial is equivalent to this coordinate representation based on these basis vector. Also, we can define a new basis. For example, v1 equal x3 minus x2, v bar 2 is equal x2 minus x, and v3 is equal x minus 1, and v4 equal 1. We can easily define each of these bases with respect to other. For example, I want to define v1 with respect to v bar. Coordinate representation of v1 is easily this one with respect to v bar 1 to v bar 4. And the coordinate representation of v bar 2 is equal to this one, this vector with respect to v bar 1 to v bar 4. And we also have v3 to v4. Now we can define the change of basis matrix P. Just put these vectors to each clone of P. Then we can easily define coordinate representation with respect to v bar with this P, because here we have coordinate representation of v, then the coordinate representation of v bar is P multiply coordinate representation in v, and it's then x bar is equal v bar 1 to v bar 4 multiply vector of 3, 5, 3, 13. That's interesting. We define a polynomial with a vector. I think this is a good point to stop. We have now covered the main idea of vector space, what they are, how to define subspaces, linear independence, bases, dimensions, and coordinate representation. This is enough for now. In the next video, we will move on to the topic of linear operators and their representation in vector space. Step by step, this will bring us closer to a very important subject, eigenvalue and eigenvectors, and the different way linear operators can be represented inside a vector space. So in the next lecture, we begin with linear operators. Thank you and goodbye.